Our next speaker, José Rafael Morán-Casal. René Morán-Casal is ready to go. Thanks very much.
Good afternoon. My name is René Morán-Casal. The subject of our study is analyzing the robustness of the temperature correction factors for water density according to API 2555 standard. I am chemical engineering working for Universidad, Nacional, and the other author, José Morán-Casal, he's here. He's a private consultant. We both have about 20 years experience in the petroleum and energy industry, and the other had the original idea. Some context before describing the study to see why the question we made is relevant and important, and why this analysis is important. The custody transfer is a method to measure the volume of liquid chemical products, and this happens every day, thousands of tons in the world, and the accurate volume must be measured because any error can have financial and legal implications. Usually, volume is measured with flow methods, but also in refineries and chemical plants, the tank inventory is made by level measurement. So the accurate level measurement is very important. The tanks are calibrated, and tables of the calibration between level and volume is made, and there are international standards to make that calibration. The IPA 5525 is one of those standards. In this example that we made a calculation, one error of 1.1% during pumping of gasoline can have an implication of $500,000 per year of losses. A lot of money. The objective of our study was to evaluate the robustness of the volumetric correction factors for water density that are included in the API 5525 standard that is used for the calibration of tanks with water as the calibration fluid. We found that these correction factors were made from an equation based on data from the late 19th century. So there is a valid question: is this standard valid today? Are these data valid today? That is what we try to find out. Currently, there are 3 applicable standards for liquid calibration of tanks. The oldest one is API 2555, first published in 1966, and it was reaffirmed by the API, American Petroleum Institute, successively, and it is still valid, it is still published. And for the US, there are now more recent standards like ISO 8222 or ISO 4269, but, and this is important, the oldest standard is still used in many countries in the world, particularly in Latin America. The volumetric correction factors of the API 9555 standard are based on a formula made by Tilton and Taylor, researchers from the National Bureau of Standards in 1937, and this was the best source of information for water density in 1966, and the original data from which that formula was based is from Chapuis in France. The measurements were made in 1891 and 1897. From 1965 and 2001, new measurements, metrological measurements of water density were made with more sophisticated methods like laser interferometry. And currently the best equation is from Tanaka et al. 2001 with an uncertainty of 1 ppm. The history of determining accurately the water density has been a long and confusing one. We will discuss this in a couple of minutes. There are many factors involved. Here I want to show you a table of the main historical actions or measurements taken during the 20th century of the water density. From this table, some of them are more important. The original measurements by Chapuis, 1891, the measurements by Kellan Whaley in 1966, the measurements from Watanabe in Japan in 1991, and finally the development of the reference meteorological equation for water density by Tanaka et al. In 2001, and additionally the development of the reference equation of the state for water, the IAPWS 95. These are, I want to show you, both relevant equations, the equation from which the tables in APA standard are based, and the equation currently used by the most recent standards, and the current meteorological equation for water density, the Tanaka et al. Equation. And if you take a look at these equations, you can see that the constants are not so different, considering that there is also 100 years of difference between them. Here we can see the original data by Chapuis at 1891. Here we see the second differences, like the second derivative, and we can see the trend of the original data. Here we can see the data or calculated with the formula by Tilton and Taylor, and here we can see the same data calculated with the equation by Tanaka et al., and you can see that there is almost no difference. You can see that they are basically identical. This is to show you that there is a base for the question we made and the study we made. How we developed the study, we calculated modern volumetric correction factors with the Tanaka et al. Equation. We calculated also the expanded uncertainty based on the Tanaka et al. Article, and it can be shown that the volumetric correction factors have an uncertainty equal to the expanded uncertainty by Tanaka. Our hypothesis was that the uncertainty of the tables, the APA 2555 standard tables, are m times the uncertainty of Tanaka, where m is an integer number. So we calculated differences of the volumetric correction factors, we calculated student p-values, and we made a null hypothesis performed for all data. Our results were that if m is equal to 1, there is a small region, we will see later, where the volumetric correction factors are significantly different. However, there is no reason to suppose that the uncertainties of the tables from 1966 or the data from 1891 is equal to the modern values, approximately 2 ppm. So if we make m equal to 2 or higher values, there is no statistically significant difference between the volumetric correction factors from API 2555 and the factors calculated with the ISO standards or the Tanaka equation. This is explained because the confidence intervals overlap. Regarding the values of the differences and values of the uncertainty, we can say that the differences are very small, usually in the 6th, 7th or 8th decimal place, while the IPA standard reports the values to 5 decimal places. The uncertainties are also very small, usually in the order of 10 at -7 or 10 to the -8. And there is a small region where the differences are smaller than the uncertainty. For a value of m equal to 1, the differences are significant only for 14 points from a total of 500 points. Regarding the factors affecting the water density measurements, we decided to make a statistical analysis. Initially, we tried to correct for temperature and correct for density, etc. But it is very complex. Why? Because in 100 years, there have been 5 changes in the international temperature standard, 3 changes in the definition of maximum water density, 1 redefinition of the liter, etc. Currently, it is considered the isotopic composition of water, the presence of light dissolved air, even the mathematical approach, and even if we use a metrological approach or an equation of a state approach is relevant. Our conclusions, the null hypothesis is accepted, and the robustness and validity of the API 2555 volumetric correction factors was verified, and the standards thus is valid, is applicable. If we want to apply it today to calibrate tanks, we can do it. A review of the history of water density measurements was made also, and I can now appreciate, and we can appreciate the skill and care of the researchers who made those measurements 100 years ago. Now we have the possibility to make a table of VCF, volumetric correction factors values, with 1 decimal more, with 6 decimal places. More accurate calibration volume tables for tanks can be made now. These tables are now available with higher precision if anyone is interested. And we now can answer your questions in Spanish or English.
Well, thank you very much. And any questions from the audience? Anybody interested in metrology? I have a question. What's the experimental technique that they used to make the original data? How does one measure the density of water to 6 decimal places?
It's very interesting because they use glass ampule with a long capillary, very narrow, so they were able to measure the expansion of the water, and from that they estimated the change in microliters in 1891. So they were very skillful in the glassware manufacturing and the experimental design.